thanks for being here today. As Manuel said, I am visiting from Tennessee, Jackson, Tennessee. I'm originally from just down the road. And I'm in Tennessee. I'm a professor of engineering, or mostly mechanical engineering is my primary focus. And so what is everybody's background here? Is your background applied math? Is your background engineering? Okay. Okay, good. How long have you been here in Aachen?
5 years.
5 years? Okay. Just 2 or 3 years? 4 years? A little bit of everything? Well, perfect. Before I start, so the talk is going to be kind of a combination of my research background, as well as there's at least a little bit of information in this course from my PhD advisor, Kurt Maute, and a course on optimization that I took from him at the University of Colorado in Boulder. And so there's some ideas taken from that course that I've applied specifically to computational fluid dynamics. And so just to look a little bit at a background check, just to see kind of if we have much of a common denominator here. Has anyone had any experience with design optimization? So you've done some work with optimization, okay. What type of optimizations?
So I did a little bit of design optimization for some courses.
Okay.
But that was more very fundamental. And then for my current PhD, I do mesh optimization.
Okay.
But for targets.
Okay.
So sort of factorization for error and so on.
Okay. So you're trying to minimize some error or by improving the mesh somehow.
Yeah.
Okay. And
yes, my bachelor's was aerospace engineering, and we had a couple courses on design optimizations. One of them was some black box optimizer and getting some parameters with risk and scope and whatnot.
okay. Okay. Well, good. And then who's had experience with computational fluid dynamics? Okay, so there's several of you that have had some experience there. So I'm going to try to start very basic in a minute, and there's a little bit of an outline here, and I will hand something out in a minute, but we'll look at kind of a motivating example that looks at drag reduction. Then we will introduce optimization. We'll look at some options for optimization algorithms. Then when we want to solve a problem, we have to do an analysis. So we're looking at some flow solvers. What can we use as a flow solver? Then we're going to look at sensitivity analysis, and then some examples of topology optimization for drag reduction. Okay. I do have a hand you can kind of follow with, and I will actually fill out these notes on my computer screen somewhat. I did want to give you just a brief background about myself. I'm here for the next 6 months. Actually, I've already been here for 3 months now. 3 more months. We'll leave January 4th. On the left-hand side is my wife. We like hiking, so we're on a hiking trail there. Those are my 3 sons, Jake, Jonah, and John Luke. They're 9 and 11. And then this is picture of the brand new library at Union University where I teach. And so it's a very nice campus. It's a small private school. My office doesn't have any windows, so I don't get to enjoy these beautiful views, but I do get to take a stroll and look at things. So as you've seen in some of the emails, I've made files available on a shared Dropbox folder. We'll use some of them. If you don't have a laptop, that's perfectly fine. I will pull up the code here. Actually, with my second computer as we need it, and then we'll look at some examples. If you're looking at using any of this afterwards, I think your handout actually has my email address on it too. By all means, I'm here for another 3 months. Stop by. I'm sitting upstairs in the guest office close to Manuel Trillian's office. So stop by there, drop me an email, and we can try to clarify questions, or maybe you come back at me and say, I can do this a whole lot better than you, and then that'd be fantastic. So we'll talk about that. Okay. So what I do is I want to kind of motivate this whole discussion by taking a drag reduction example. Okay, and what we're going to do is we're going to consider a laminar low Reynolds number flow. Basically what that means is the fluid is flowing very slowly. It's going to be steady state. There's no crazy transient effects happening. There's no turbulence. So we want to keep our flow very simple at this point over a circular object. Okay, so if we have something like this, we have a circular object, and we have a constant velocity inflow around this object. We can apply a pressure or a density at the outlet, and we have some radius. Okay. Now we can compute the flow across this circular object, and we can calculate the drag, which is going to be some function of the velocity, the density, and the radius of this cylinder. Okay. So the drag is kind of the resistance that the object provides against the flow. So we have flow coming from the left-hand side, moving to the right, and that flow is going to have to avoid the cylinder. And so if we define this problem as an optimization problem, we might want to say, let's minimize the drag, which is some function of the density, the velocity, and the radius. And our design variable at this point would be the radius. Okay? The question is, how can we change the radius to minimize the drag of this object? Okay. Basic object, what do we know? What happens if we have drag and we have a radius? How does the drag change with radius? It will somehow increase with increasing radius. So let's just put it in here like this. And now, if we want to minimize the drag, we just get rid of the cylinder. So that would be the trivial case, and it would be pointless. But obviously, if there's no object in our flow, then there's no resistance, and so there's no drag. Now that would be a pointless optimization problem. And so typically, when we look at optimization problems, we add something. We say there's going to be a constraint. Okay? Also, we typically have more design variables, and we'll add more in just a minute. Okay? So if we have a constraint, well, what could be a constraint? So let's say we have this cylinder, and this cylinder has to house something. Let's say the cylinder represents the wing of an aircraft, and we need to be able to fit a fuel tank in there. We need to be able to fit, let's say, a wheel assembly that has to be able to be housed under the wing. So there might be different things that we need to be able to fit into that wing. And so we might be able to say, well, okay, the volume of this wing or this cylinder, or maybe the surface area of this cylinder, has to be greater or equal to some value. Okay? So what we can do then is we can say, well, okay, now let's plot this as well. So if we draw another axis on the right-hand side and we say this is volume, okay, maybe the volume will change as pi r squared. Okay, so the volume is going to be increasing somehow like this. And so let's say we have a volume right here of 0.008. That means our cylinder has to be at least this big in order to have enough volume. So we now have a constraint on our design so that everything on the left-hand side of this violates our constraint. Because here's how volume increases with radius. Here's where the volume is 0.008. If the radius is smaller than this value, our volume is going to be smaller. And so that violates our constraint because our wing are not big enough to house whatever we want to place in it. Okay. So based on this, the optimal design or the optimal radius would be right there. We want to minimize the drag. We know that we can minimize the drag by decreasing the radius. But now we have this constraint, and the constraint limits how far we can reduce the radius. Okay. But that's still trivial. Okay. So we don't need to have a complicated design optimization algorithm or problem. So at this point, this would just be a basic, it would be referred to as size optimization, because we just have a size of an object and we change the size of the object. We don't change the shape and we don't change the general layout or topology. We only change the size of this object. Okay. So we can take one step further. Okay. We now want more design variables. So what's something that we can do? We could go and we can say, well, let's take this same flow, but now let's have an ellipse. And this ellipse has two axes, A and B. Okay, so we use an ellipse. Where now we have two design variables, A and B, that we can change. So now we can actually change the shape. By varying A and B, we can go from a circle to an elongated ellipse or a flat plane. Okay. Now we will actually have different ways, different combinations of A and B will have our minimum volume of this 0.008, because the volume now of an ellipse is pi a b. And if we draw a contour plot where we just try different values of b, different values of a, okay, and we calculate the colored lines, that's the drag. So drag decreases kind of in this direction, where the lowest drag is kind of out here. And then the volume are these lines right here. So a volume of 0.008 is this blue line right here, meaning that everything below that blue line has a volume smaller than our constraint. So all of this violates a constraint. And now we would want to find, well, where is the minimum drag in this region above the curve of 0.008? And in this case, we'll find that, well, it decreases right here to 0.2, 0.15. The smallest value is somewhere right here. So actually having a very flat A and a very long B is going to be the best result. And so you can, that's somewhat similar to the shape of the wing of an airplane. So you have typically an airfoil on an airplane has a fairly elongated profile. Now, our optimum would then be kind of right here. That would be an example of shape optimization. Okay? But obviously this is a very simplistic example of shape optimization. We only have two parameters. We could take this shape and we could parameterize it with multiple points. So we could have some shape like that starts out looking kind of like an ellipse, and we could use several points along its, and at every point we could move this point y1, x1, y2, x2. So we could have these 6 points. We could map some spline, some curve that connects these 2 points based on the coordinates. And our design variables could be the x and the y coordinate of each one of these points. And now our optimization could try to find the best coordinates of these, the best combination of these total of 12 values. The problem with that is that we can't plot it and look at it nicely. And so for now, we'll look at these two design variables, and will later become more general when we look at topology optimization. So now the next question is, how can we further generalize the optimization problem? We would like to have an even more general design space, posing the generic question: what object will minimize the drag subject to our constraints? Okay, so what object? Okay. So if we have our flow state, well, maybe this is best, having two objects in the flow. Probably not, but maybe. Okay. We could have a biplane or bi-wing airplane. Okay. And any of the options that we had before, the size optimization would not allow for us to get a result like this. There's nothing that we can do to change our ellipse into suddenly becoming two ellipses. Okay. And so what we need is we need to have a more general approach, and that's referred to typically as topology optimization. Okay. And there's a couple different ways to achieve this, but one option is to say, okay, we have this problem, and now somewhere within our design domain, or within our problem domain, we have a design domain. Usually we use a regular grid because we don't want to push our solution towards any given solution just based on how we chose our grid or our mesh. And then at every point in the mesh we have our design variable, S1, S2, S3, all the way to Sn. And then each one of these points we can change to it either being a solid or it being fluid. Okay. And so now if we have all these design variables, and they can all change from being solid to fluid, and we can do this continuously, so it's not either all solid or all fluid, it could be something in between, and that something in between might be porosity. So let's say we use a sponge, and so we can have every point here can be a sponge, and that sponge can either have big holes and not be there, or it can have smaller and smaller and smaller holes where at some point it becomes a solid. And so mathematically that will then allow us to continuously change any point in our fluid from a fluid to a solid, or back from a solid to a fluid. Okay? And so if we have something like this, that would be a material distribution based approach, or Ersatzmaterial if you're looking for the German word. Then we can suddenly have a design pop-up right here and a design pop-up down there, which wouldn't happen in this case, but it could happen in general. Okay. Questions, and if there's questions along the way, please ask questions. So that kind of motivates the overall idea. And so what we're going to do is we're going to take a step back, and we're going to look at optimization algorithms. Then we're going to apply them to a basic shape optimization problem. Then we're going to go and say, well, okay, now we actually want to solve a fluid problem. We want to set it up so that we can do topology optimization. And then we're going to run a couple topology optimization examples. Okay. Okay. So this might be a little bit of repetition from about, but we can take an analysis problem, okay, and that's oftentimes defined as having some residual. So we have some residual, and this would be a typical residual in a structural analysis problem. In a structural analysis problem, you have a stiffness matrix, a displacement, and a force vector, but you can really typically change any, if we write a partial differential equation in terms of a finite element algorithm, we would define a residual to reach the point where that residual reaches 0. Okay? And so U are our state variables. That might be a pressure and a velocity if we have a fluid, but it could just as well be a displacement if you have a structure. It could also be, there's also optimization going on in the finance world. So it could also be maybe U is some distribution of stocks. Okay? And you want to optimize the stocks that you own to have the best return. Now things become more interesting because now we're making money and stuff, abstract fluid dynamic things. But what we can do now is we can augment this into an optimization problem by introducing a design variable. Okay? So we change this. So now our residual becomes a function of U and some design variable S. And typically, in many cases, the design variable S goes into the stiffness matrix. It could also have an effect on the force vector, but typically it goes into that stiffness matrix. Okay. And then we can distinguish again between size and optimization. If we have some initial design, if we just make it wider, that would be size optimization. If we parameterize the boundary and we can change the location of each of these points, that could change the shape. And if we could have islands pop up, that would change the topology. And so that would then be topology optimization. And again, this is an illustration where we can take every point in the domain, we can either make it solid or fluid, and that would then represent our new flow problem. Now, if we have a design variable S that can vary continuously, okay, so S can vary continuously, then what we can do is we can use gradient-based linear or nonlinear programming approaches. And when you're dealing with fluids, it's always nonlinear. So it's nice to have linear problems, but always nonlinear. And then if the design variables are discrete, then we're limited to more general approaches. And thanks. And so of a more general approach might be a genetic algorithm. Okay. It's called a genetic or evolution algorithm. Or just straight out brute force. Okay? So what you can think of here, this is actually really interesting, and I guess that's where the name comes from, but you have these evolutionary algorithms, and so let's say you have 10 design variables. You pick 2 pairs, basically a mother and a father, that have 10 different attributes, and now you use a random number generator to choose different algorithms from these 2, from the mother and the father. You pair them up, they generate offspring, and then you test. Oftentimes you might pick 10 offspring. You test those 10 offspring, you see which one is best, or the 2 best, and you pick those 2 as the 2 new parents, and then you repeat the process. Okay? And which I don't have much experience with genetic or evolutionary algorithms, but if you're looking at industry applications of design optimization with fluid dynamics, oftentimes they use evolutionary algorithms, because if you're looking at the airplane, and they're very effective if you only have a few design variables. Okay? So you can apply an evolutionary algorithm if you want to improve the shape of an airplane wing, and you maybe you define 3 or 4 parameters that govern this shape. In that case, it's computationally feasible to use an evolutionary algorithm. If you use a topology optimization problem, and this mesh would be way too coarse to represent an airplane. So if you had an airplane, maybe you'd had a mesh of 10,000 by 10,000. So now we have, what do we have there? 100 million design variables, and you're not going to be able to use an evolutionary algorithm with 100 million design variables. If you have 10 design variables, by all means, you can do it. Okay. So our focus will be on the gradient-based linear, nonlinear programming approaches. And we can then define a general optimization problem where we want to minimize some objective, some goal, Z, and then we can have different constraints, inequality or equality constraints. Okay. And so, just to give another visual example. So let's say I have my wallet here, okay, and it's just too heavy to carry around. The objective could be, I want to figure out a way to decrease the weight of my wallet. Well, one option would be is that I just hand you all my change. That's going to decrease the weight of my wallet. But that's where my constraint comes in, because my wife is going to say, hey, I want to use that money to go hiking somewhere. I don't want to pay some graduate student in Aachen. And so we'll have some constraint that says that the amount of money after I improve the weight has to be greater or equal to the amount of money when I started. Some equality constraints, like my wallet needs to have my Personalausweis in it. It needs to have my credit card. So there might be some things that can't change. Okay? And so you can think of constraints as some of those things. So now I want to figure out, well, how can I reduce the weight while keeping my credit card in there and my Personalausweis, and while having afterwards more money, or at least the same amount of money than before. Okay? And so I can run to the bank and change all my change into notes, and I guess then I'm better off. Or I can put all the money in the bank and say, well, now it's all in the credit card. And so when we then look at this, when we formulate, we have to consider the feasibility of that we have. So we need to be careful that we don't define some ill-posed problem so that our constraints actually make it impossible for us to solve the problem. Because it could be that you have 2 conflicting constraints. You could have, if you define 2 equality, and those would be obviously conflicting, but sometimes they're not as obviously conflicting. If you have 2 constraints, one constraint says, I need an equality constraint that there's $100 in the wallet, and the other constraint says, also equality, that there's $50. There cannot be exactly 50 and exactly $100 in the wallet. That's just impossible. So now we have conflicting constraints. if we draw this out, we can draw, for example, let's say we have two design variables and we have an unconstrained problem. Now, these might be contour lines, and so z would be decreasing in this direction. So this problem is unconstrained. There's nothing that keeps us from moving in a decreasing direction of z, and so we can perform this optimization problem. We could also have feasible constraints. Where we might have something like this, S2, S1, and now we have our z again, same z. Okay. And now we might have G1, which says that everything on this side is not possible. And then we might have a second control. G2. Everything outside of this circle is not a feasible design, but everything here in this red region would be feasible. Okay. So those would be feasible constraints. And then we could also have something like, well, and so this would be infeasible because it's impossible for us to satisfy this constraint and that constraint at the same time. And so that's something that you, when you're defining an optimization problem, that you have to watch out for a little bit, because sometimes if you run an optimization algorithm and it's just spitting out answers that don't really make sense, it could be that, well, maybe you've given it some constraints that it's impossible to satisfy these constraints, and it's trying to jump back and forth between these two constraints, trying to satisfy them. Okay. Detail, but I just wanted to make sure that you're kind of aware of the possibility of something like that happening. What we do want to look at now is we want to take a look at, briefly look at an unconstrained problem. Okay. So when we have a problem like this, okay, and we're starting out at this black dot, okay, how can we find the optimal value of the design variables in this problem? We want to find the optimal value of S. How can we do that? What? Okay, so gradient, or even more general, it's just like if I want to go from Aachen to Köln, what do I need to know? Well, I need to know a direction. Which direction do I need to go? And I need to know how far is it going to be. Because if it's, I don't know, 100 kilometers, I might take the bike, I might take the car or the train. If it's 10 kilometers, I might get the bike. If it's 50 kilometers, I might still take the bike, but now I'm going to pack a snack. Okay, so I need to know how far is it, and in what direction do I need to go. Okay. So we need to know the direction and the distance, or step size. And so one way, and there's different options for all of these. One way is to use the method of steepest descent. And what we can do is we can just find the gradient, Pin, is equal to negative the derivative of our objective with respect to Si. Okay. So that gives us a gradient, and that gradient would give us, right here, P and N. And now we need to know, well, how far do we need to go in that direction? Because if we go too far, we're somewhere out here, and we're not better than we are where we started out. Ideally, we'd like to end up right there. Okay, but probably in this case, if you're using a gradient-based optimization algorithm, you'd probably end up in this little valley, which would be called a local minimum. Now, mathematicians sometimes get all tied up into, well, if you can't prove that you have a global optimum, why bother? Well, in engineering, typically, if we can decrease the fuel consumption of our aircraft by 50%, that's great. At that point, we really don't care, is this a local optimal or is this a global optimal? We're 50% better than we were before. Now, if we could get 60% better by finding the global optimal, great, but our first concern is, can we be better than we started out with? Okay. And so one way that we could now avoid or try to find this global minimum is to try to solve the same problem with different starting points. Okay. So you would seed this problem differently. One time your starting point might be right there. The next time you might have a starting point right here, and you'd solve this problem several times with different starting conditions. And then you can come to 2 or 3 or 4 different solutions, and you can see, do they all converge to the same problem, same result, or do they converge to different results? If they converge to different ones, you'll have local minima or local optima, and then you can pick the best one of those, and you typically can't prove that that's the best result, but if it's better than what you had before, that's usually a good answer. So for the direction, or for the step size, we can use a line search. We could also use something like a bisection method to see, well, okay, we know this direction. Let's try several different points to figure out along that direction what's the best value. Okay. At this point, we'll just use a line search. And there's alternatives to this method of steepest descent and a line search. For example, you could use something more advanced. You could use Newton's method. If you use Newton's method, you really get direction and step size all in one, but you need more complicated derivatives, and you might have to find the inverse of the combination of your derivatives. Okay. And so you could also use a conjugate gradient method. So there's different options. At this point, we want to keep it simple. We just look at the method of steepest descent and a line search. Okay. So this then leads to the following procedure, where if we know the direction and the step size, we can update our design variable and then we can iterate, and we can run this through several iterations and find, hopefully, our optimal solution. Okay. Now, if we have a problem like that, okay, and now the problem is constrained, okay, almost all realistic problems have some constraint. Now we need to figure out, how do we consider this constraint? Okay. One option is to use what's called the penalty method. And so we define a new objective, z star, which is just z plus some penalty multiplied by our constraint g. Okay. So we have a constraint g, which is maybe the volume, and constraint is satisfied, this product will be 0, but if the constraint is violated, we take this violated constraint, we multiply it by a penalty and add it to the objective. So if we're trying this objective, we want to minimize z, well, we'll want to get rid of this penalty. So if this guy is satisfied, that will eliminate this term, and then we can minimize z. And so that would be a penalty approach. And we'll talk about this a little bit in a minute, but we're not going to focus on that. An alternative would be to use a more general approach, which is by taking our optimization problem and we write it as a Lagrange formulation. And this is analogous when you end up solving adjoints. That's where you can write a Lagrange formulation for different applications. And Lagrange for Si eta j gamma j is equal to z, which is a function of our design variables only, plus now the sum over all, this would be the and we'll look at a figure in a minute, but the optimal solution is a saddle point or the stationary point of this Lagrange function. And we'll look at visualization of this in a minute. What we can do, if we want to find the stationary point of this Lagrange function, we need to take its derivative with respect to all of its variables and set it equal to 0, because that's where the stationary point is. All of the derivatives are 0. Okay, that's basically our equilibrium point. Okay. So we can do that. The resulting conditions are called the Karush-Kuhn-Tucker conditions. Okay. And so what we get is that we need the gradient with respect to S of z, plus, now we have that summation, eta j, gradient of S of h, plus the summation gamma j, gradient of S g. Okay. So that has to be equal to 0. Now the second condition, if we take the derivative with respect to the derivative eta j, which is one of our dual or Lagrangian variables, we get hj is equal to 0. And now this last one are the inequality constraints, and we can also find gj is equal to 0. But we can also generalize it, because if we have an inequality constraint, meaning that we want to show that g is smaller or equal to, I don't know, some value. Okay. If g is smaller than this value, we're fine. Okay. So we don't want to penalize our result if g is smaller than the value. We only want to do that when g is greater than this value. Okay. And so whenever g is not violated, gamma actually will be 0. So we'll set this gamma parameter equal to 0 in that case. So gamma has to always be, gamma is greater or equal to 0, and so we get gamma j, gj is equal to 0, okay, is our third KKT condition in this case. Now, these KKT conditions are necessary for the optimal point, but they're not sufficient, meaning that it's possible to find a point in your problem where these terms are all 0, but that's not your optimal. And so in addition, you need your problem to be locally convex. You need there to be some valley, some minimum that you can go to. And that would mean that the Hessian, and I'm not going to get into that because I'm in engineering and we try to avoid Hessians. And so if the Hessian must be positive definite. So only if the Hessian is positive definite, then you know for sure that these KKT conditions are actually at an optimal point. At what it looks like, or what this Lagrange function looks like for our drag reduction example. So we had this example right, this is the right page? No, we had it right here. With this example right here, this plot was actually generated with a lattice Boltzmann-based fluid dynamics solver, and it took some time. I think it took about 10-15 minutes to generate this plot, to analyze enough points so that I can plot this contour plot. Now, alternatively, what I'm going to do next to illustrate the next few things is, well, what happens if we can take this problem and we can just approximate this drag with some function? And I thought, hey, I'm smart, I have engineering books. I know my engineering textbooks actually give me some tables that tell me that for laminar flow, meaning relatively low velocity flow, except not quite as low as this, I have different coefficients of drag for different aspect ratios of my ellipse. So for different ratios of A over B. I thought, well, okay, I'm going to take those, I'm going to map a function through them, and then I have a nice analytical solution for this. And the analytical model came nowhere close to matching the results earlier from my computational fluid dynamics code. So I thought, oh, okay, how else can I come up with an analytical model that works fairly well? And so I actually ended up, in the end, looking at these, and I thought, well, okay, I have a fairly straight line here that has a little bit of a belly up, so I can map it with a parabola of some sorts. Okay, so I knew, well, I'm going to have some parabola here, and then A goes in this direction, and so it varies some as a function of A. It increases with A primarily, and so I used trial and error to kind of come up with a function that matches the function on the earlier page very closely. So if you compare, I think it was this page. So if you compare this contour plot with this contour plot, they match very closely. In this case, the optimal result is actually here. It's not out there. But it matches very closely, and it will be sufficient for our that we'll use here. Okay. So at this point, I do want to quickly, let's go over to my computer. This one actually, Matlab license here, I need to be logged into my computer or into the campus in Tennessee. And so I have Matlab running on the other laptop, and so we'll look at in a second. Okay. So this is this analytical function right here. This is a volume. When I run this code, and you can find it all, there's the directory that I shared is RWTH, short course materials. And then there's some subdirectories. This first one is going to be in the subdirectory analytical ellipse. Okay. And all I'm doing is I'm varying A and B, and I'm looping over that, and I'm evaluating the force of volume, and then I'm drawing a contour plot of the result. So if I run this, draw this contour plot, I get this contour plot of the analytical function, and right here would be the optimal. At least graphically we could represent the optimal. As soon as we have more than 2 variables, we can't graphically find the optimal anymore. But at this point we have 2 variables, we can graphically find the optimal. Now I'll write down the Lagrange function in a minute, but what we can do now is we can also, if we define the Lagrange function for this problem specifically, we can plot the Lagrange function. And so here's our algorithm. And so this is really, well, the Lagrange function is, let me bring it down just a little bit. Okay. The Lagrange function right here is just the objective plus eta times the constraint. And so what I can do now is if I say I have 2 variables, a and b, and my Lagrange variable, so that really gives 3 again. I don't like plots in 3D, that doesn't work well. So we'll freeze b and set b equal to its optimal value. So the optimal value for b is 0.0841. And now if we run this, we get a plot right here. And this plots the Lagrange function with varying gamma and varying a. And our optimal solution is a saddle point right there of the Lagrange function. Okay. Now in 2D that's nice, and we can look at the plot and we can pick out the optimal result. But we can still use this when we have more and more design variables, because mathematically the meaning of a saddle point doesn't change whether we have 2 design variables or whether we have 100. So mathematically we find that saddle point when we reach those KKT conditions, and they're equal to 0. Okay? And so if we can write some algorithm that can get our problem to where we find this saddle point, then that should be at least a local optimal solution. Now there's something else that we can do is we can actually plot. Well, let me go back to this. So generally what we see is this is a, so that's our design variable. Our saddle point is in the general direction of minimization in the direction of the design variables s, and the direction of the dual variables, or basically our gamma on our constraint. And this will become important in a minute. Now we can also find the optimal, and I kind of zoomed in. We find that if we have this minimum and maximum, we can really draw the gradients. We can define the gradient of our Lagrange function with our variable a, and the gradient of our Lagrange function with respect to the variable gamma. And now we can define h, which would be dl dA squared plus dl d gamma squared. Okay. Gradients should be 0 at the saddle point. So if all the gradients have to be 0 at the saddle point, but they're non-zero away from it, we need to have our function this h would have to have a minimum at the optimal solution. And sometimes visually it's easier to find a minimum in a graph than to find a saddle point. And so all plot this, and we would then find the minimum right there. This would be our a value, which actually turns out to be the optimal is 0.0303, and then we find our optimal gamma value, which is about 0.1, and we'll look at that in a minute. But this is just for visualization, illustration purposes. So let's go back to slides right here. Okay. So now we can write, and well, I'm not going to write down the Lagrange function at this point, but we can now identify the saddle point as we did on the board right here. So that's the optimal location, the optimal solution. Okay. And it's a minimum in A and a maximum in gamma. So we want to minimize in this direction, and then we maximize in that direction in order to find this optimal location. Okay. So now we need to figure out, we have our Lagrange function defined. How can we now solve the optimization problem? Okay. And there's different options. Okay, one option would be to use what's called a primal method. So if we have the Lagrange function is a function of our design variables S and our dual variables gamma and eta, depending on whether we have equality or inequality constraints. And primal methods, they search space of the primal variables. So they search in the design variable space. Okay. And one option is a basic penalty method. Okay. A benefit is that we simplify our problem. If we use a primal method, we usually simplify our problem to an unconstrained problem. A disadvantage is that our constraints are usually only approximately satisfied. Okay. So if we use a primal method, our constraints, let's say I have a constraint that I want to have the same amount of money in my wallet that I had before, but I want to have less weight. A primal method, let's say I started with $100, a primal method might say it's okay if I end up with $99. $99 is basically like $100, that's fine. And then I can ramp up my penalty parameter, and if I use a higher penalty parameter, well, maybe now I need to have at least $99.50 or 99.9 euros. So search in the design variables to an unconstrained problem. The constraints are only approximately satisfied, and the choice of the penalty condition is difficult. Okay. Dual methods search in the space of the dual variables of gamma, so the dual variables. And they're efficient for a small number of constraints. So when we have problems with a low number of constraints, dual algorithms are usually efficient. And what they do is they convert the problem into two problems: a maximization in the dual variables and a minimization in the primal variables, and we look at that in just a minute. The third option is to use Lagrange methods. And Lagrange methods simultaneously solve our problem in the KKT conditions in order to get the result. And so a benefit of the Lagrange method is that for the optimal result, our constraints can actually be violated. And so there's some benefits to the Lagrange methods. They're the most general ones to some extent, but they're oftentimes also the most costly ones. And so we're going to focus on dual methods. But if we actually take this problem, and we can look at right here, these KKT conditions, these are just three equations for three unknowns. If we take those and we solve them directly, that would basically be a Lagrange method. Now, if we have a more complicated problem, so this is really a function that includes the drag, and finding the drag might involve the solution of a computational fluid dynamics program, which has its own residual, and so we might have to satisfy the residual equations for our problem plus these KKT conditions, and if we solve them all simultaneously, then that would be a Lagrange method. For this problem, it was easy to do. You could even do it by hand, and if you solve those three equations by hand for A, B, and gamma, you get A is 0.0303, B is 0.0841, and gamma is 0.1040. So now let's take a look at dual methods. Okay, so dual methods are named after Uzawa, and there's a book from 1958. And what we do is we start with this Lagrange function. So we have our Lagrange function, and we change our problem into an outer maximization. Okay. So what we have in gamma, where we have the maximization based on changing the variable gamma of phi of gamma j. And then an inner minimization in S. So now phi for a given gamma j star, so now gamma is not a variable anymore, gamma becomes a constant, is now equal to the minimum of the Lagrange function of Si gamma star. Okay. So what we do is we say, well, if we find phi for a given gamma as being the minimum of the Lagrange function, we can then find the maximum of this phi to find the correct dual variable gamma, and then the combination of those two will give us the optimal result. Okay. And we can take this back to the visualization. We maximize the problem in the direction of the dual variables, and we minimize it in the direction of the primal variables to get to Lagrange, or our saddle point of the function. Okay. And so this is our algorithm. Okay. Now what we can do is we can return again to our drag reduction example. We set B equal to 0.0841, and we want to just prove that this thing works. Okay, we want to show ourselves, instead of just believing this, let's just look at whether or not this works. So our Lagrange function for this problem is A, gamma is 0.01, A to the 1.5, 2000 plus 200, B optimal over A minus 1 squared plus gamma 0.008 minus pi A times B optimal divided by 0.008. Okay, and the reason why we divide it by 0.08 is because we want to kind of the size of the constraint to be roughly the size of the objective. So we don't want this to be a tiny number and this to be a big number. Typically, you want them all to be kind of, so you will normalize your values. Now we have max of phi, function of gamma, and then phi gamma star is going to be minimum, looking for A of L A gamma star. And for our problem, we have 0.01 is smaller or equal to A is smaller or equal to 0.1. And gamma, we've said before, has to be greater or equal to 0 because we're using an inequality constraint. If our optimal design is bigger than the required volume, we're fine, because we can still fit the fuel tank if the wing is bigger, if that happens to be the lowest drag design, which it's not going to be. So now what we can do is we can look at this problem. And we can solve it basically with a brute force approach, just 2 line searches in both directions. If I can log back in. Oh, there we go. Okay. So this next code is located on a dual algorithm, simple dual test. So if I go under the short course materials, dual algorithm, simple, dual test. So what I'm doing is I have a function that evaluates phi. Okay. This function that evaluates phi, okay, right here uses a line search. It basically calculates a gradient, which I can calculate analytically. It passes the function evaluation, the initial value for A, and the gradient into a line search algorithm. This line search algorithm uses LEval, and LEval does nothing other than evaluate the Lagrange function for a given gamma and a given A. Okay. And if I run this program, dual test right here, it solves very quickly because it's all analytical. And we get a gamma value of 0.104 and an S value, A value of 0.0303. Okay. And just for interest's sake, I counted how many times in this process we evaluated LEval, so our Lagrange function, 2,490 times. I'm sure that there's we can tweak some of the parameters on our line search, and maybe we can have a less stringent convergence criteria, and we can run this and we can have fewer evaluations. But either way, function many times. Okay. So you can play with this a little bit at your own leisure, but this is basically a brute force approach where if we evaluate phi, this does the inner line search to minimize the Lagrange function by finding our S value, or the outside right here, we do another line search, okay, and we maximize the function for gamma. Okay. So 2 line searches nested, and we can solve our dual algorithm. That's not how we do it. And we already alluded to the reason. Well, what are the challenges with the dual methods as we applied it right now in the line search? Well, first of all, must be solved repeatedly. simple because our L got evaluated by a basic analytical function, but this L could be the CFD analysis of an Airbus, which might take 2 weeks to run on a supercomputer, and then if we have to evaluate it 2,490 times, even if you can improve the performance of the Airbus a little bit, or Airbus, not Boeing, see I'm in the US and we have Boeing, but Airbus is not going to be interested in your approach because 2,490 times 2 weeks on their supercomputer, first of all, that's going to be years and years, and it's going to be so costly that whatever saving in fuel economy you're not going to get back with this approach. Okay? So the inner problem must be solved repeatedly. Often L SI gamma is costly because we have a CFD problem. Outer problem, okay, must typically be solved iteratively. And so oftentimes you might use something like a penalty conjugate gradient method. And so our solution now is, well, instead of using the line search on the outside, we use a penalty conjugate gradient method, which is a little smarter than just a line search. So does anyone know, what does a penalty conjugate gradient method generally do? Any idea? So a line search, I give a line search a gradient, and this gradient might point in this direction, and the line search is going to do a line search in that direction, and it's going to find how far do I need to go in that direction, and that's the point. Now, if I have a problem of many, I can have multiple. And so if I get the gradient, for the first step in the penalty conjugate gradient method, it will work just like a line search. So the first time it will work as a line search. I'll walk in this direction. Now, the next time, I'm going to get a gradient, and the gradient might point in this direction. Well, the penalty conjugate gradient method is going to say, well, okay, I've already searched it in that direction and found the best step. So no need to go any further than that. So I'm just going to take the normal to that direction, which in 2 dimensions, all I have is 2 options that I can search in. But if I have 100 variables, I can have all sorts of directions. So now instead of searching in this direction, which is part of the direction that I've already searched in, I'm going to just take the normal to it. I'm going to just search in that direction. So I'm going to take directions that I search in that I have not previously searched in. And so it's a little smarter than just a basic line search. And then approximate the, because the inner problem is very costly to solve. And each time that we solve it, we only improve our problem a little bit. And so why don't we approximate it? So if we approximate it with a simple Taylor series, which would basically tell us that, well, z gamma is approximately equal to z as I plus dz dsi delta si. And this would be a linear approximation. And so if you find in the literature that something might be called sequential linear programming, then that refers to this approximation as being approximated just as a linear first order term Taylor series approximation. Now, if we go a little bit further and we make an approximation that's analytically solvable, okay, and convex in the vicinity of Si, okay, what we get is what's called a sequential convex program. Okay. And so we'll do the, I'll write the equation down in a minute, but let's look at the visual illustration of this. But if we have a problem that might look like this, where we have Z and S, and our actual function might look like this. Let's say our first point is right here, and now we get an approximation of this based on the gradient, okay, and the value at that point. We approximate this somehow here as a local convex function. We have a solution to this function just based on knowing this point and the gradient. So if we have this as an analytical function, we can find this point analytically. We can find this point analytically without any more function evaluations. And now we're right here. Now, once again, we can evaluate our function to get the function value and the gradient. This process, so now we get an approximation that looks like this. Our minimum is right here. And so now we already get very close to that optimal of our function. Yeah. So this would be approximation 1. And then this is approximation 2. And then we can take more steps. Okay. But each one of them, we approximate our costly function L with an analytically solvable convex approximation of L in the vicinity of S. Okay. And so what this means is we have Z of S is equal to Z evaluated at the design variable state Sn, so the previous result, plus the sum of I positive, and I'll explain that in a minute, dz dsi evaluated as at Sn, siu, which is the upper limit, minus sin, which is the result squared, or the S value squared, divided by siu minus si, which is a new optimal, minus si upper limit minus sin, minus, and now we take the sum I comma minus dz dsi evaluated as n, and now we have, well, there should be extra set of brackets right here. Okay. Sin minus sil over si minus sil minus, there should be squared right here, minus sin minus si. Okay. And the details are not that important. You can look those up in some of the references on the Dropbox folder if you're interested in them, or you can just blindly use the SCP algorithm, which I did for years. But if you look at them, this is the underlying function. This is a term, and so what we want to do is we want this function to be convex. Whenever this gradient is positive, dz ds, we use this part. When this gradient is negative, we use this part of the approximation. That's to make sure it's always convex, so that when we find the minimum, we can find the minimum of that function. Okay. The details are not that important. Okay. Now, if we, and that's the last thing we'll do before we return to the drag reduction example. Okay. And we now solve it with a sequential convex program, SCP. What we get is the following. We get we have this in the folder SCP Analytical, and there's function. No, that's not. That's actually the SCP algorithm, which kind of describes some of its inputs. But if we take test ellipse, what we need to provide the SCP with is we need to give a function that evaluates our objectives and constraints, okay. Func2. Func2 evaluates the objective z and the constraint g. And right there's the functions, the analytical functions for those two. Okay. Now if we go, and we also need to give it the derivative of those functions. So d func2, right here. In this case, we only have two design variables, so there's only two derivatives of z, which are given right there, and two derivatives of g, which are given right there. And then we give it the initial value for our design variables, the upper limit, the lower limit, the maximum number of iterations, the convergence limit, and these are basically, it uses on the inside a system called, or an approach called the method of moving asymptotes. And so basically, I'm starting with an S value, and I'm only allowing myself to search if my full design space is out here, but I know I'm only having a local approximation, so I'm only allowing myself to search within limited asymptotes of my starting point. And so I can make those asymptotes wider and smaller, and those parameters, those typically work fairly well, but those parameters, that's what they accomplish. So if I look at this, right here, it's kind of described what these different features do. And the last thing, use SED, UMI, dump, I'm not, but it's something that one of the postdoctoral students added to this algorithm. I've never used it, so the input value for it is just 0. And when we then run this test ellipse program, we evaluate it, and we get exactly this. Now we actually did it in 2 dimensions. So we solved for both A and B. We got the same gamma value, so same A, same B, same gamma value, and the total evaluation count of L was only 40. So instead of solving L, our CFD problem, 2,540 times, or how many times it was, now we're down to just solving it 40 times, which is much better than 2,540. And so this SCP algorithm is a nice tool when you're doing design optimization. And to be honest, when I worked on my PhD research, I used the SCP as a black box. So I used it, and I gave it Z, DZ, and DG, and I basically didn't care what happened on the inside, as long as it spit out better results than I had at the beginning. And so the goal here was to provide you with a little bit of insight into, well, how does an SCP optimization algorithm work, a sequential convex programming algorithm work, but not really to provide you with enough information to where you could go and write your own. Yeah. But I did provide the references on right here. If you go to selected references, MMA, SCP, so you can look at some of the original references for the SCP and the MMA optimization algorithms. Or I encourage you, if you're dealing with any type of optimization problems, just try out this SCP, give it your function, and see if it spits out good results. Yeah. What we're going to do after the break, which I think we'll have a 30-minute break. Is that how it usually works? I think. Okay, so we'll have a 30-minute break. After the break, we're going to look at, well, okay, what can we now use as a flow solver? And then how can we get this flow solver to give us all of the necessary inputs that we need to solve a problem with the SCP? So we need to have a flow solver that spits out the objective Z and the constraint G. And we also need a flow solver that gives us the derivatives of those. Okay? And it might not always be possible to, well, in some cases we might be able to use finite differences for the derivatives. Sometimes that's too costly. And so we then need to do an analytical sensitivity analysis to come up. So now we want to look at, we have our optimization algorithm, and as I discussed with some of you in the break, there's by all means there's alternatives to the SCP algorithm. The SCP can also sometimes you might observe a problem where it seems to converge towards an optimal solution, but it doesn't hit. If your convergence criteria are too stringent, it might not hit the convergence criteria, and it will then continue past the optimal, and it will start diverging. Okay. And so that's something that I've experienced as I prepared my materials for today. Is in order to allow us to solve some of the optimization problems within a few minutes instead of a few hours, I had to decrease the mesh density. And so that meant that the program didn't converge to as high of an accuracy, and so it didn't stop, and then it would just kept converging, and then it into a solution that really made no sense. And then afterwards I came back to my computer and I looked at it, and then afterwards I realized, oh, it actually got to an optimal, but then it just kept going, because it was like he told me I need to get an optimum that's this good, 10 to the negative 6, and it didn't find it, and so it got to the best point, and it said, well, I have to go somewhere to try to make it even better, and it went somewhere off. At that point, it just kept going and got worse and worse and worse. And so I'm not exactly sure mathematically where the reason is for that divergence in the SCP, but that's something that you want to watch out for just a little bit. But let's take a look now at flow solvers. Let's see. Right here. Okay, so we want to now choose a flow solver, and we need a flow solver that allows us to evaluate Z and G. Also the derivatives, we need dz, dg, that's not the derivative we need. We need dz ds and dg ds. Okay. We also need to be able to change from solid to fluid and vice versa. We need to be, it needs to be somewhat efficient, because we need to solve it many times throughout the optimization process. And so something that we found when I started my work as a PhD student was that the Lattice Boltzmann method has some of those attributes. And so I'm not endorsing the Lattice Boltzmann method as a solution for all of this world's problems, as some people might. But when I started my PhD program, it looked to us as the simplest way to do this because it's a fairly simple algorithm. It has an easy way to actually add this porosity to change from a solid to a fluid. It can be implemented in parallel very easy because of its structure. And it inherently uses immersed boundary methods, which when I started my PhD program, I did not know anything about immersed boundary methods. And so I thought, well, this is super cool in the Lattice-Boltzmann method because we can do this. And then later on, the more you look around, there's immersed boundary methods for everything. So you can accomplish the same thing. And we now use Navier-Stokes-based solvers for flow topology optimization. We use some moment method-based solvers for topology optimization. And so you can do it with any solver. But in this case, the Lattice-Boltzmann method, I think, is a nice, easy implementation. And when I teach at the university that I'm working at, I primarily teach. I kind of do research as my hobby. And so the majority of my students are undergraduate students. And I have a fourth semester undergraduate class. And in a lab, within 3 weeks, all students implement their own Matlab-based Lattice-Boltzmann solver. And I don't think I could have them do that with a Navier-Stokes-based solver because the math involved would be too complicated and the programming involved in Matlab would be too complicated. But they can do it with the Lattice-Boltzmann method. And so we'll use the Lattice-Boltzmann method for the demonstration's sake here. We also, just because I know that we have a lot of moment method people, at least in this building, I want to at least give a brief look at the Lattice-Boltzmann method from the Boltzmann equation to the Lattice-Boltzmann method. I'm just going to skim through that. And so anyone that's really interested in this can look at some more notes that I've uploaded. But this right here is the Boltzmann equation. Okay? And so the Boltzmann equation is basically f is a distribution function, and it is in physical space and velocity space and time. And so the distribution function is actually a 7-dimensional variable. Okay? It can vary in velocity in all 3 directions from negative infinity to positive infinity. That's the most difficult part to solve. It can vary in space in the x, y, and z direction, and then in time. Okay? And so solving the Boltzmann equation directly is not really feasible in most cases. And so what we want to do is we want to resolve, or we want to expand the velocity space, okay, which is this. We want to resolve that and basically get rid of the velocity space, or we want to discretize our velocity space. And so what we can do is we can take a moment, okay, we can say f is equal to this term 1 over 2 pi e to the negative c squared over 2, and now we sum ai, well, there should be an hi, where these are Hermite polar. And so we really expand this distribution function as this term, we approximate it as being equal to this term plus, and then we can make this summation. These are constants, and these are polynomials. The higher the order of our polynomial, the more exact we are. And the lower the order of our polynomials, the cheaper our model is. Okay? And so what we can do, just for simplicity's sake, is if we take this equation, okay, we want to expand this in moment space. So we want to integrate from negative infinity to infinity of our polynomial hi multiplied by the Boltzmann equation. Okay. dxc. If we do this and we use polynomials up to second order, okay, do this and we evaluate it, we recover the Navier-Stokes equations. Okay? And you can, if you're interested in this, talk to Dr. Terrellian up on the 4th floor. He is the expert on these moment methods. And so check with him. But if we do that, we recover the Navier-Stokes equations. 2 is we can recover macroscopic quantities, like the density is the first moment of f. So if we integrate over the velocity space, just 1 times f integrated over the velocity space, we get the density. Okay? And so basically, if f is a function that there exists a particle with a certain velocity within our space, then if we integrate over all velocities, we've captured all particles, and that would be the density of the material that we're dealing with. Okay? The velocity, or really the momentum, is going to be the integral of the x velocity multiplied by f integrated over this velocity space. Okay? And so if we think of the idea that we can start with the Boltzmann equation, if we replace the distribution function with this moment expansion, the Navier-Stokes equations, and if we integrate it with respect to these factors, or we integrate it with the macroscopic variables, density, velocity, forth. Okay. Now, at this point, instead of actually doing this integration, we can use Gauss-Hermite quadrature. Okay. And so what we can do is we can say that the coefficients can be said to be equal to the Hermite polynomials hi times f d xi. But that's also equal to a Gauss-Hermite quadrature, the integral over all the quadrature points, wj divided by 1 over 2 pi, and the details are really not that important. This is just for illustration purposes. Hi xj f x ci t. So is we can take this integral of a moment with a distribution function to recover the macroscopic variables. Now we also say, well, instead of doing this integral, which goes from negative infinity to positive infinity, go over all velocity space from negative infinity to positive infinity, summation. Okay. And what we choose our Gaussian quadrature weights, which is 9 weights, and these velocities, we can exactly recover the second order moments. Okay. So these second order moments right here to then get Navier-Stokes. If we, instead of taking the moments and using continuous functions, if we choose our coordinates correctly in velocities, we can just evaluate our function at 9 points of accuracy and approximately recover the Navier-Stokes equation. Okay, so what we can then do is we can think of this as at any point in our computational domain. So this represents just one point in space. We have an f1, which is, that's the number of points that are stationary. An f2, that's the percentage of the particles at that point that will move to the right side. So that it will move in this direction. This is the particles moving in that direction. The particles moving diagonally. And so we have particles, we basically have the fraction point that moves in the 9 different directions, including the stationary point. Okay? And what we can do then is we can take this And we do a finite difference discretization in time and space. Okay? So we can get this equation and we can discretize it in time and space. Okay? And then this is the right-hand side where we have this collision term, Fj equilibrium. That's basically how fast, if we light, let's say we capture all the air molecules in this volume, and now we just let them collide with each other, how fast do they reach equilibrium? Or what is the equilibrium state that they will reach? That's given by, in this case, what's called the Maxwellian equilibrium equation. Okay. Now, we're not going to the whole short course on the Lattice-Boltzmann method, but the important thing is that this equation, it can be split into a local but nonlinear collision step, which is Fj at x comma t collision is equal to Fj x comma t minus 1 over tau, and this tau can be shown to relate to viscosity. It basically says how fast are we converging towards equilibrium. The higher the viscosity, the faster we'll be like honey sticking together, so the faster we'll converge towards an equilibrium. And so we have Fj xt minus Fj equilibrium xt. Okay. And we'll have a global but linear streaming or propagation step. And so the collision step just says at one point in space, what happens when these particles collide? The propagation step is, well, how do these particles interact or communicate or move to other places in space? And this step is global, but it's linear. And it can be given by Fj at location x plus ei delta t, t plus delta t, is equal to Fj collision at x comma t. So within one time step, the result of the collision step here will move to this location. Okay. And then the last component that we have is the equilibrium distribution, which is Wj rho 1 plus 3 Ej dot product with u plus 9/2 Ej dot product with u squared minus 3/2 u squared. And at this point, well, there's lots of literature that you can look at, but basically solving this system of equations on a mesh will approximate the same solution as solving the incompressible Navier-Stokes equations. And there's literature on that, and I'll let you look at those if you're interested in it. But at this point, I just want to quickly go over how you would now implement Boltzmann solver. Okay. So we'll do that. And again, we have a goal in mind, and the goal is not to be Lattice-Boltzmann experts. The goal is to have a flow solver that we can then use for design optimization. I guess this tries to protect me in that when I type in my password, it doesn't like for me to have it hooked up to the screen. Okay. So if we go, there's a directory in the notes. Let's close all this mess. Okay. There's a LBM basic, okay, and this is really all it is. So if I go in here and I open LBM basic and I run it, I'm just going to run it real quick just to see. It will run and it does 100 iterations. Well, it's not very pretty, but you can basically see streamlines. This would be flow around a cylinder. Obviously, the mesh is very coarse. I have 10 points in the x direction, 30 points in the y direction, but you can see some basic streamlines over an object. This algorithm really just consists of two main components plus boundary conditions. Okay. So if we look at this algorithm, so at the beginning we just set kind of the viscosity, we define the size of our problem, but then we have this iteration routine. So we have a while loop. While the number I is smaller than 100, we go over all coordinates, and then here we have the collision step, and there we have the propagation step. So what the collision step does is, if I open this up, okay, it calculates the macroscopic properties. The density is just the sum of all f values. Okay. Then it calculates the momentum, which is really f times the velocity in the x direction is the ux momentum, and f times the velocity in the y direction is the uy momentum. Okay. And then here's the weights from the Gaussian quadrature, and here it calculates this equilibrium distribution function, and then right there we perform the collision step. Okay. So this is very explicitly written, and it basically it's the implementation of exactly the equation right here in the notes, and this equilibrium distribution function. Okay. Now, whenever we have an inlet, let's say we have an inlet, what we want to do oftentimes is we want to prescribe, we want to say, well, we want to have this velocity at the inlet. Okay, so all we can do is we take the same collision function, but right here, let's say we want to prescribe a velocity in the y direction, we just overwrite the calculated velocity with the velocity that we want it to be. So that would be an inlet condition. And there's more precise ways of doing it, but this is the easiest way to implement it. At the outlet, we might want to have a pressure boundary condition, which pressure is related to density by the ideal gas law. And so we can also use a density boundary condition. So we calculate our velocities, and then we simply override the density with whatever density we want at the outlet. So in this case, we just make it 1. And so that would prescribe the pressure at the outlet. Okay. And then we have boundary conditions. So we have a solid boundary. Well, and if we're looking at particles, here we have. So let's all, okay. And I have particle start. Particle is, so there's a node on the other side of the boundary. There's going to be a particle that's moving from here to there. Well, what will happen when it hits the boundary? It depends a little bit on the boundary properties, but if we have a no-slip boundary condition, what it's going to do is, this guy, it's going to hit the boundary and it will reflect back. Okay. There's going to be also one that will move in this direction. It's going to hit the boundary and it will actually be reflected back. And there's also going to be one that will move in this direction and it will be reflected back. And so all particles that tend to hit a boundary will just be reflected back by that boundary. And that's, in the Lattice-Boltzmann method, referred to as a bounce back boundary condition. And that's what we do right here. So basically what we do is we say that we have, let me find, okay. We have F1, F2, F3, F4, F5, F6, F7, F8, and F9. Okay. And these guys are just F9 becomes F7, F6 becomes F8, F8 becomes F6, F2 becomes F4, so they're just reflected in they came from. And so that's really what we do right there, is we basically just say F is equal to the old F, but the different entry points. So we have these 9 different velocities, and we just reflect them. Okay? And then we have the propagation step. And the propagation step, what it does is, it says, well, okay, if I have these 9 what happens? But the F2 will move in the positive direction. F2 at t plus 1. Okay. F6 will move up here. F6 at t plus 1. F4 and so the way that we can implement this is, if we're looking at this code right here, let's look at the first line. What this does is we just say all F2s, oh, no, there I did something I didn't mean to do. All F2s, we move them from location 1 to Lx minus 1 into locations 2 to Lx. So we move every F1 one location over to the right. Everywhere in the mesh, all at once. The only thing we don't do is the end one at the end, well, it doesn't go anywhere, it leaves the computational domain. And the beginning one at the inlet, well, there's nothing that comes in, it gets replaced by the inlet condition. Okay. So those are the basic steps to the Lattice-Boltzmann method. Now, I want to point out a couple things. So if we run this, and this goes well beyond the Boltzmann method, and the goal is not to be Lattice-Boltzmann experts here, but if we solve this, okay, you can use a tool in Matlab called the Profiler. Has any of you worked with Profiler in Matlab? Okay. If you have not, and you use Matlab, it's a very powerful tool. Okay. You can turn on the profile viewer, and you can run any code that you want to execute. So let's run LBM basic. Okay. It's going to run this code. It's going to spit out the results. Okay. And then it's going to tell me how much time or its function, okay, and how many times it has called each function. Okay, so in this case, we've called the collision function 20,988 times. And we've solved this problem on a very small mesh, and we've only iterated 100 times. So we're not anywhere close to really converging this problem. And so what would be some possible options? Because if I tell you now, if we wanted to solve this problem and we would want to get a reasonably accurate answer, we would want this mesh to probably be 100 by 500, and we would want to run 100,000 iterations in time instead of 100 iterations. Okay? And we would be here 2 or 3 weeks from now if we execute this code. What would be some options in Matlab to make it go faster? And this extends well beyond this little Lattice-Boltzmann code. This is just some general tricks of the trade. How can you make MATLAB go faster? What type of a programming language is MATLAB? It's all vector and matrix based. And so MATLAB, if you have a loop in MATLAB, that's the least efficient thing that you can do in MATLAB. If you give MATLAB a loop, because MATLAB, all MATLAB functions are written so that they can operate on vectors and arrays and matrices. And so if you can change these loops to actually vectorize your MATLAB algorithm, that would be one option. And we can look at it right now. So if we go at the analysis option and we look at LBM fast, what I'm doing here, and I'm sure there's, for the computer scientists in the room, I'm sure there's much better ways to do this, but what I'm generating ahead of time is I'm generating a list of all bounce back conditions or all collision coordinates, x and y. And then I'm passing this into this new version of the collision function. And what it's going to do is it will evaluate the collision step for all these points all at the same time. Okay. So now if I solve this problem, LBM fast, I think this is basically the same problem. There's the result. It's a little different because the fast version, the slow version uses a constant inlet velocity at the bottom. The faster version actually uses a parabolic inlet velocity. So the results are a little different, but here the answer comes almost instantly, and it will be much faster, well, comparably faster when we increase the problem size. Okay. So one option in MATLAB is vectorize your code. Don't write loops over a lot of variables. If you can use matrix operations or vector operations, use those. What are some other options that you can do in MATLAB? Has any of you run a C code from MATLAB? All MATLAB functions are actually C functions, but what you can do is you can use a MATLAB code. Let me find one. I think it's right here. So what I've done in here is I've actually I've gone and I've replaced this loop of doing bounce back collision and all of that. I've replaced it with a C function. And I can actually, MATLAB has a tool called MEX, and you can compile a C function and you can pass information into a C function, run a C function, and then pass information back to MATLAB, which can be helpful in a variety of ways when you're doing research. And one way that it's helpful is that oftentimes when you're writing a C code, you don't necessarily want to write all your input-output stuff. And MATLAB has lots of nice graphing tools and those sort of things that you might not want to mess with when you're first prototyping a new code in C or C++ or whatever other, or Fortran or Java or whatever you want to do. And so it can be very helpful to write a C function within MATLAB, call that C function, but then plot your results in MATLAB. Okay. So that can be something useful. And there's an example here. Look at it or ask me questions afterwards if you're interested in it. And another option is there's also parallel implementations of MATLAB. And you can do GPU programming in MATLAB as well. I've tried that. At one point, I had a working GPU Lattice Boltzmann code. It was kind of a pain to use. And since my research goal is not to come up with the fastest possible Lattice Boltzmann program, but to do optimization stuff with Lattice Boltzmann, I've kind of dropped that by the wayside. But if you're interested, there should be some that you can download for free online, like Lattice Boltzmann GPU MATLAB programs that they're interesting to look at. Yes?
One question about the basic one. So it looks to me like F, or each iteration, F is updated by using other parts of F. So it seems to me this would depend on the iteration order here.
In which here? In the propagate?
The main
Okay, in this loop, yes. So, well, okay, so
why is it not a problem?
because, okay, all of these are local operations. Okay, so if you think back about the key features of the Lattice-Boltzmann method is that the collision step, inlet and bounce back and outlet, they're nonlinear, but they're local. So they only happen at that location x and y, and they only care about the f value at that location x and y. Okay.
I mean,
so I'm
this explicit f current step and f next step. So if the first row has already been updated and now working the second row,
yes.
so I'm mixing current values from the first row with old values from the row below.
Well, but no, because so what I'm updating is I'm updating everything at this location, which only the bounce back or the inlet or the outlet or the collision, the f only depends. So I'm really only updating this x and y location of this f, and I'm going over all points, and so I'm updating really everywhere all x and y values with the collision step.
Will they not use the f values from the neighbors?
No, that happens only in the propagation step.
Oh, okay.
Okay, so only the collision step and the inlet, outlet, and bounce back is entirely local.
Okay.
Okay.
I thought it was a little bit less local.
No, it's entirely local. It's completely local. And then the propagation step is the only place where you now move stuff to the neighbors, and then you go back to the next collision step, and so now the neighboring nodes collide with, now the new information has moved to this point, and those new 9 values will collide again, and you kind of repeat the step.
Okay, fine. Thank you.
Yes. Any other questions? Okay. So what you do want to do, and so that's in this other program, is you do want to if at all possible, improve the performance of your Matlab code, or if you're working on a larger code, you probably won't implement it in Matlab, but oftentimes, at least in engineering, I found it very helpful to prototype what I'm trying to do in Matlab, because debugging is fairly easy. I can quickly graph things, and so I use Matlab quite frequently. Now there's a couple other things, let's see, that we need before we look at, before we actually look at this Matlab code and we add it to our SCP algorithm. One thing that I didn't want to include in the notes, and you will just be using it, my chalk somewhere. It's going to be pieces of chalk all over the room after I'm done. But what we've looked at is we've only looked at the basic bounce back boundary condition. So basic bounce back says that the wall is halfway between this, and whatever travels in this direction, it will go here, it will be reflected, and in the next time step, it will move back to right there. So whatever starts here at ft will end up right here at f t plus 1, basically. Okay. So that's the basic bounce back condition. Now, if we want to accurately represent our ellipse, we will have some sort of a curved boundary, and this is not going to be located halfway in between. And so there is a condition that you will see in the code that's called interp bounce back, and if you look at the Lattice-Boltzmann literature, it's called interpolation bounce back boundary condition. Basically, it finds this location and says, well, okay, here I have this node that moves towards the boundary. Here I have another node. Okay. And so if the boundary is closer than halfway between these two nodes, then the reflected value will be interpolated between this value and that value, because this one will move this direction, this one will move, and so the resultant value will be actually somewhat of a combination of this one and that one. So you're doing interpolation, and you can actually come up, or at least the Lattice-Boltzmann literature displays it as a second order accurate boundary representation. Okay? So that adds a little bit more detail or accuracy on our boundary. The second thing that we want to know, we want to be able to evaluate the drag. Okay? So if we have our ellipse, we want to know what is the force that's acting on this ellipse. Okay? Well, what happens here? This F, the sum of all F values that travel in the x direction is really the x momentum. Okay? So if this F, in this case this would be F4, hits this wall and is reflected, okay, that really is a momentum exchange at this boundary. Okay? So if I sum this F and that F value up over this wall, that's the force that this wall experiences along this link. Now there's an additional force along this link and along this link at the boundary. But basically, in essence, what I can do is I can identify all boundary points, and I can then sum up the forces or sum up the distribution functions that interact and bounce back from the wall in order to compute or sum up, evaluate the total drag on the surface. Okay? And so now I have to punch in my password again. Okay, so if we look at this code right here, is that the right one? No, that's the basic ellipse interp. What you're seeing is I'm identifying this interpolation bounce back boundary condition. So I have this function for everything that's inside of, I guess that should be, yeah, inside of the ellipse. It's an interpolation point, and then I basically find this function, what it identifies as all the links with the fluid. So with nodes that are solid and nodes that are in the fluid. The detail is not overly important. And if I now go and I run this, let's see, I will we'll get back to the nodes in just a second. What I can do now is we can take this program and we can solve it as a shape optimization problem. So if we go to the algorithm called LBM shape opt, and we open the program ellipse opt, okay. Ellipse opt now uses a lot, rather than using the analytical model which we used earlier in the course, we now use the Lattice Boltzmann method to evaluate the drag of the ellipse. Drag ellipse. Okay. Drag ellipse, okay, calls the Lattice Boltzmann program LBM ellipse interp with given A and B values. And it then performs or uses the Lattice Boltzmann method. It sets up initially how big is my mesh, how many points am I using in each direction, which points are boundary points, which points are interpolation points, which points are inlet, outlet, and collision points, and then it performs or solves the problem right here with, in this case, the C implementation of the Lattice Boltzmann method. But I can go in here and I could change this and I could uncomment, comment, and then now I've changed it from using the C implementation to using the Matlab based implementation. Okay. Then I also have the function ddrag ellipse. So what do I need for my SCP? I need a function that gives me Z and G, and I need a function that gives me the derivative of Z and the derivative of G. Okay. So if I take the derivative of ddrag ellipse, in this case, because I only have two variables and I was too lazy to implement the analytical derivatives, I'm just using a finite difference evaluation of this function. So all I have is 2 design variables, and so with basically, really I could have implemented it with only 2 extra function evaluations or 2 extra solutions of my Lattice-Boltzmann program. I can get all the derivatives that I need. Okay? And I just use simple finite differences where I evaluate everything at the original S locations, and then I perturb the S value slightly, evaluate it again, and calculate dz and dg using finite differences. Okay. Now, let me see if I can undo this so that we can solve it quickly. Now, when I run this, this should solve the, actually, ellipse opt. This should solve the shape optimization problem for the ellipse. Okay. If I run this, we can actually see here, the values at the top, these are A and B, but they're in Lattice-Boltzmann units. So you can follow down here, you can kind of see the iterations converging kind of towards a result. If you wanted it to converge more closely, you could increase the number of iterations. Okay. And you can now see it updating the A and B, and it's going to update them both initially, okay, until we satisfy our constraint. And then once we satisfy the constraint, this should take about 3 minutes or so to solve. Once we satisfy the constraint, you will see the 2 values differ. You see them differ slightly right now at the top, and that's when we do the finite difference evaluation of our gradients. And then you'll see them, well, now they're both already different. Okay. So now they've started we started to have A smaller than B, so we're starting to get this longer and squished down a little. And so we'll see in a minute, the results should look familiar. And again, just just skim the surface with this Lattice-Boltzmann algorithm. But the idea is really the idea that if you're working on some problem, well, this would be your analysis algorithm, and this would be your derivatives. If you're more interested in what goes into the Lattice-Boltzmann algorithm, by all means, come see me upstairs over the next 3 months. Drop me an email, and I can point you in the right direction. Okay. So this is converging now. We can actually see. So at every iteration, it prints out some basic informations. The objective, the constraint violation. So basically the constraint is satisfied. How much have the design variables changed from the last step? Basically not at all. So this is a KKT residual. Okay. Well, I guess this is actually the final result. So we have converged at this point. The residual is minimal. Our S values, this is the A value. It's 0.0255. The B value is 0.1. And this is the gamma value down here. Those values differ slightly from what we had before. Yeah. But that's because before we used our analytical approximation, and there's a little bit of a difference between the analytical model and what we solved here. So let's pull up my slides again. So we had, if we run the program LBM analysis, LBM ellipse wrapper, that gives us this contour plot, which is a contour plot using the Lattice-Boltzmann method of varying A and B, drawing the contours for the volume, and then drawing contour lines for the drag. And we would find that the minimum drag would be right here at this corner, which is at B equal to 0.1 and at A somewhere smaller than 0.03. And those are the results that we just found. We found the results that when we used the solver, we found A is equal to 0.0255, B is equal to 0.1000, and gamma is equal to 0.0219. So the results are similar, but as would be expected, not equivalent to our analytical solution that we found earlier. Now we could adjust this. We could use a finer mesh. In the Lattice-Boltzmann algorithm, we would change Lx, and I'll point that out in a minute. We could also use more iterations to converge it more tightly. So the next step then is how can we now perform topology optimization? Let's see. I think I need to start with this page. So in topology optimization, what we want to do is we want to be able to change every point in our computational domain from fluid to solid. And as I mentioned earlier, what we can do is we can basically use the idea of a sponge and a porous material. So if we take porous material, okay, we just need a simple tweak to the LBM algorithm in the collision step. And what we do is we simply replace the velocity with this term. Where kappa is equal to 3 works well. So if we have this value that goes to 1, okay, when the porosity is 0, okay, we just use the velocity calculated in the program. When the porosity is equal to 1, okay, 1 minus 1, our velocity is set to 0. And so we're basically, we're in essence dissipating all the energy with a porous material. And so what that allows us to do is we can basically represent an object with a porous boundary, a solid inside, and a fully fluid outside. Okay? Obviously, that representation is not super exact in the boundary region, okay? But in many topology optimization problems, that would be acceptable. Because what you want to do typically in topology optimization is you want to get a rough idea of what might be some good design choices, and then you're going to take that, parameterize it, and perform a shape optimization with a much more detailed and much more precise algorithm. Okay. So going back 2 pages. When we have topology optimization, we typically have, and we briefly talked about this during the break, we have a couple different ways to represent our boundary. One one option is kind of to use this local, and you refer to it as voxel-based or element-based, material-based representation, okay, where we say right here that at any point, okay, we know this point is either solid or fluid, and we have this regular grid. And what we can then do is we use this Brinkman penalization, where we use this density idea, or this porosity idea, in order to represent the shape. Okay. Alternatively, we can use a more approach, okay, where we use level sets. Okay. So we use a higher dimensional function. So if we're looking at a 2D problem, we usually have a 3-dimensional level set. So we kind of have this mountain range, and we say we cut it off at some value. Okay. Slice it off. And wherever we slice it off, that's the geometry that we represent. Now we could take this slice, and we could then represent it back with the porosity-based approach. Okay. But alternatively, we can take this slice, and we could do a body-fitted mesh. Typically, we don't do body-fitted meshes in topology optimization, because that would mean we'd be constantly remeshing. Okay. Or we can use an immersed boundary type meshing strategy, which if you're familiar with finite elements, that would be like a CutFem or extended finite elements, where basically you can locally refine, or you can add additional degrees of freedom close to the boundary so that you can put the boundary where it actually is instead of along your predefined mesh size. Okay, so there's several different options. I want you to be aware of those. For now, for simplicity's sake, we're going to use a porosity-based approach. A lot of research is now going in the direction of using level set-based methods with these immersed boundary conditions. And the reason for that is that oftentimes interesting physical phenomena are governed by boundary phenomena. And so if the boundary phenomena, what happens at the boundary, if that's really important, so let's say you're looking at turbulence and you have boundary effects due to turbulence, if you represent the boundary with some porous sponge, you're going to lose everything you've been interested in. And so you can't really use that porosity-based approach. If you're looking at very well-behaved laminar flows that are at low Reynolds number, low velocity, then the error that you get due to this porosity on the boundary is minimal, because the boundary is not going to be the driving factor behind your result. Okay. So if we do this, this is just a repetition again, if we use this porosity-based approach, and this is some results that were shown in my PhD work, we can actually show that while it's not exactly the same, but if we change the radius of a cylinder, the direction, whether we do a porous approach or whether we do it with an interpolation bounce-back boundary condition, very much the same trend. Now the results are not equivalent, and we kind of zoom in here a little bit more, but they follow very much the same trend, which is really what we're interested in for design optimization. Okay? If they follow the same trend, but they differ by a couple %, they're still both going to point towards the same optimal solution. Okay? So that gives us a boundary representation. Now, if we look back at the SCP, well, what do we need? We need Z and G, and we need DZ, DSI, and DG, DSI. Okay. For the shape optimization, okay, for shape optimization, example, we used a finite difference approach here to get our DZ DSI and DG DSI. Okay. But now, if we represent our problem like this, okay, and our shape optimization we solved on a mesh, I think if I remember it correctly, I think the mesh is like a 30 by, it might have been a 30 or a 60 by something. So it may be a 30 by 100, 3,000 points, okay, 3,000 nodes, and at each node we have a porosity, a design variable. If we wanted to find those with finite differences, we'd have to evaluate our function 3,000 times, and so that's just not feasible. So we need to come up with an analytical way of computing these sensitivities. We need to develop an analytical sensitivity analysis so that we can evaluate a function that spits back all these sensitivities instead of having to do a finite difference-based evaluation. So what we can do is we can define a performance function, f, okay, which can count for both objective and constraint. Really, we need these derivatives, these gradients, for both objective and the constraint. And the derivation is equivalent for both of them. So let's just have a general performance function f, and then later on we can let f be z or let f be g as we need it. Okay? So what we can write is we need this derivative df dsi, which is the partial of f with respect to si plus the partial of f with respect to lowercase f. Lowercase f were our state variables in the Lattice-Boltzmann method. Okay. If you'd be solving this problem for Navier-Stokes, you would have df dsi is equal to df dsi plus df d rho transpose d rho dsi plus df du transpose du dsi. And then if you had maybe Navier-Stokes 4 years, so you had temperature included, then you'd also have a plus df d temperature dsi. In the Lattice-Boltzmann method, all our state variables are the terms f, and so we have this partial with df dsi. Okay. But due to design variables si and the large number of state variables f, okay, this term is very costly to compute, and it's advantageous to utilize an adjoint approach. Okay. So what we want to do is we want to define an adjoint approach for our problem. Okay. So we have the following problem. Okay. We want to minimize some functional f which is subject to the solution of our Lattice-Boltzmann residual. And the Lattice-Boltzmann residual is ms, f minus f is equal to 0, where this is a collision plus a propagation. So this is just an operator that and one propagation. The residual, which basically tells us our Lattice has to be converged. Okay. So we have f and the residual. Okay. So we want to minimize the drag subject to the constraint that our flow problem is actually solved. Okay. Because we don't care if the flow problem is incorrectly solved, our drag is meaningless, so whether or not it's minimized doesn't really matter because our result is incorrect. Okay. So if we have this problem, we can now again write a Lagrange function. And that's basically what I think what you do probably when you do your mesh optimization of some sorts. So you write a Lagrange function f s comma f plus your Lagrange variables or your adjoint variables are s comma f. Okay. So now we kind of apply this residual as kind of a penalty. So we write a new Lagrange function for our Lattice-Boltzmann algorithm. Okay. We can write AKT conditions. Okay. So the KKT conditions are dl ds is equal to df ds plus lambda t dm ds is equal to 0. It's equal to dl df, which is equal to df df plus lambda t dm df minus I is equal to 0. dl d lambda is just equal to r s comma f is equal to 0. And this just tells us our flow problem has to be converged. Okay. So now we have the first equation is what we're really interested in, which uses these adjoint variables. Okay. The second equation, we can now actually solve for these adjoint variables. The third equation, as long as we converge our flow solver, that third equation is satisfied. Okay. So if we take equation 2 and we solve it for lambda, what we get is lambda is equal to I minus dm df inverse transpose df df, which is equal to the inverse transpose Jacobian of our Lattice-Boltzmann system. The inverse transpose Jacobian df df. So this is a Jacobian of the Lattice-Boltzmann system. Okay. And this is the adjoint equation. Okay. And then we can plug that in to the first equation, and we get dl ds is equal to df ds plus J inverse transpose df df transpose dm ds. Okay. And the costly part is typically this inverse of the Jacobian. Okay. Now, if you actually look at this problem, if we try to solve J transpose lambda df df, okay, and we now were to apply an iterative Jacobi algorithm to this. So if we apply in Jacobi, what we get is lambda I plus 1 is equal to d inverse the diagonal of the Jacobian df df minus j minus dj transpose lambda I. Okay, so this would be a Jacobi algorithm to find our adjoint variables, where this d is the diagonal of the Jacobian, and so the inverse of the diagonal is free, basically. Now, what we can realize is that in the Lattice-Boltzmann method for LBM, dj is approximately the identity matrix, approximately. So then lambda I plus 1 would be equal to df df plus j minus I transpose lambda I. It should be, the I should be at the top. This would be an equivalent model to the transient adjoint Lattice-Boltzmann equation. Okay, and so there is an analogous equation to the Lattice-Boltzmann equation. That's the adjoint Lattice-Boltzmann equation, which you can solve iteratively for the adjoint variables lambda. Okay. But because it's possible to do that with a Jacobi algorithm, and typically we know that a Jacobi algorithm is not the most effective way of solving a sparse linear system, that really begs the question, well, what would happen if we would explore things like a GMRS or a multigrid or some other solver for a sparse linear system? Could we come up with something more efficient than what's currently done in practice? Okay, but this is kind of an aside. What we do in the code that I give you is calculate the Jacobian. We take the inverse of it, even if it's costly. We take the inverse. We plug it in here. We solve for the derivative dl ds. Okay. The Jacobian really is just a combination of the Jacobian of the propagation step and the Jacobian of the collision step. Okay. And because of the nature of the Lattice-Boltzmann algorithm, okay, this has a very nice structure. So if we look just at the collision step, be a one-dimensional Lattice-Boltzmann which only has 3 functions at each node. If we had 9 functions at each node, the collision step Jacobian will give us a block diagonal structure, which would be a 9 by 9 in 2D. In 1D, it's a 3 by 3. Then the propagation step will simply shift rows in the collision Jacobian. So if we combine this, the collision step and the propagation step, we can calculate the Jacobian of the collision step. The propagation step will shift rows in that Jacobian. And then we have our Jacobian. We need to find our inverse. And we can then proceed with our analysis. Okay. So what I want to do now is I want to pull up the Lattice-Boltzmann program. I spent the last 20 minutes, let's see, looking at drag reduction topology optimization. And I think your handout has kind of the inputs, and I've actually provided you with variable or with settings in this code for 3 different optimization problems. Okay. So the optimization code is in LBM opt. Okay. And when you run this, it's important that you set the whole directory into your path. Okay. So in Matlab, everything we've had so far, all functions that we used were in the same direction as the function that we executed. Okay. In this case, there's subdirectories, and there's an SCP algorithm. There's a GCMMA as an alternative. We'll look at an example in a second. And then there's a fluid solver, which has the Lattice-Boltzmann code underneath it. And then there's some utilities, kind of the input file, the driver file. And then there's some level set stuff, which I have disabled at this point right here. But it's still kind of in the code, but there is a level set function, but I didn't want to deal with it for the purpose of this talk. So what we want to do first is we want to set our workspace, set the path, and so we want to add the LBM opt directory and all of its subdirectories to the Matlab path, which means that from anywhere within Matlab, you can now call the functions that are in those directories. Okay. And now we have 2 functions that we typically modify. The in file and the driver file. Okay. Typically, the driver file is where we execute the program. The input file is where we can make some changes. Okay. And so there's some basic settings, and I'm not sure what decrease this just for the sake of time. Okay, so the basic drag optimization problem that we've been dealing with, I've solved with this settings. So we solved it on a domain, the size domain. So this is the lattice Boltzmann mesh. This is the level set mesh. What it actually ends up doing is we have one design variable in between. A grid like this, I have nodes, lattice Boltzmann points right here, and I have design variables right there. And at each lattice Boltzmann point, I'm actually taking the average of the 4 neighboring design variables. And the reason for that is so that the result gets smoothed a little bit instead of having very jumpy points. But you could do it without this averaging as well. Okay, so that's why these are different. So if I wanted to make this on a smaller mesh, let's make it a 19 by 19. Not sure how well that will work, but we'll find out. 19 by 19, 20 by 20. Then, right now, you only have the option of a lattice Boltzmann solver, but there used to be a Navier-Stokes solver linked up with this. You can set the Reynolds number, the reference length for the Reynolds number, so let's make it 20, because we've decreased the size of the mesh. Let's pick a Reynolds number of 10. Typically flow over a cylinder. When do things become unstable? Transient. Any? What? No, that's flow inside a pipe. Then it turns turbulent at 2000. But flow over a cylinder, usually when you go 50 or above, you get the vortex, von Karman vortex street behind the cylinder. So let's keep smaller than that. We want a steady state problem. Okay. This relaxation parameter, that's kind of related to the viscosity, but we can leave it as is because we're looking at Reynolds number. So as long as the Reynolds number is fine. Let's see what other settings we have. These are level set settings, then they're irrelevant at this point. Now the important thing is when you vary this, when you change this function, this is the input file, you don't want to delete any rows even if they're empty. Because there's a read function that reads from this file and reads it into Matlab variables. And if you delete a line, it's going to offset everything. Okay, so then here you can define number of constraints. We only have a mass constraint. This is a volume constraint. So we want to say how much of the volume can be fluid, how much must be solid. So if I set this to 90%, that means that 10% has to be solid. So I have this big volume of fluid, and I want 10% has to be solid. Okay. And let's see, is there anything else that's important? Let's look at it for now. See if this works. There's this driver file, for which does a lot of setup initially. And then what I do right here is this piece of the code, and I described it in your handout. Main is this. Okay. And now I'm going to say inside there's some box, and this box is my design domain. Okay. So what I'm saying right here is there's an area right here of 5 cells, 5 cells, 5 cells, and 5 lattice nodes. And those nodes are prescribed. They have to be fluid all the time. Only this middle region am I allowed to change, or is the optimizer allowed to change. Okay. And then down here, it then calls the SCP optimizer And as an alternative, you can just try the GCMMA as an alternative to the SCP optimization algorithm. So when I run this, I execute this code. See if it all works. Okay, these are the initial conditions. That's just the initial porosity distribution. Let's see. So there you can kind of see the algorithm converging, something in my Linux. So now we can kind of see right there. Now you have a velocity distribution kind of around this cylinder, and obviously we don't have a high quality solution here because our mesh is 20 by 20. But you can see the velocity distribution around the cylinder. And now in a minute we're going to see, well, what's it going to do at first? Okay. At first, our volume is going to be less than 10% of the overall domain. So it's going to increase the porosity of that region in the middle, and it's going to make it more and more solid until at some point we've reached 10% of the overall region. Okay. In this case, 10% is going to be, this might not work out well. My boundary along the outside is too big. Let's kill this for a second. Let's decrease the size of the boundary block a little bit. 3, 3, 3, 3. When I scaled the domain smaller, I didn't make my boundary box smaller, so my 10% was basically the whole middle had to be solid. So run it again. Okay, now we have a bigger box where our design can be. Okay, and we can watch this performance optimization. You know the settings for two other problems in them. One is, and they're both traditionally used in topology optimization problems through our literature. One is a nozzle, so you have an inlet along the whole side. You have an outlet just 1/3 of the outlet side, and then you want to know, well, okay, what is the shape of the nozzle that will lead to the lowest amount of drag or pressure drop? And so it will optimize the shape. The next one is you have an inlet on the left-hand side, you have an outlet at the bottom side, and you now want to know what is the channel, the bent channel that will lead to the lowest amount of drag. And you can actually, if you look through the literature, you'll find that the lower the velocity, the more of a straight channel you get, and the higher, the more you increase the velocity, the more of a bent channel you'll get for that example problem. And so the settings should be in there, so you can kind of see right now we're already starting to form. Not everything is constant, so you're starting to see a changing shape down here. That shape might not turn out to be exactly the same as the shape that we have in the notes. I don't know if you have this shape in the notes or not. This was the shape that I got when I analyzed it on a slightly larger, bigger mesh. We'll see what happens here. Leave it down here. Looks like we're actually getting a round ball on this smaller mesh. We'll see if it will make it a little bit flat and elongated. Okay. One thing that you can already notice here is that this is more than likely my design domain is too close to the exit, and what it pushed out the back of the computational domain and wants to against the back so that it doesn't really have time to impact the flow until the flow gets to the outlet. But you can kind of see it starting to elongate a little bit like like an ellipse there. Any questions while this is running? I know the second part was a little bit more rushed, and we kind of jumped through the Lattice-Boltzmann method as a tool, but think about it really just as you're using the Lattice-Boltzmann method as an example of really any other flow solver that you could plug in its place, or any structural analysis problem, or any, I don't know, whatever the problem that you have is, you can basically, if you can evaluate Z and G and its derivatives, you can use it as inputs into the optimization algorithm, as long as it's a somewhat convex problem. Yeah, now we are actually getting somewhat to kind of a little bit of an elongated ellipse type solution. Now, all of this is, let me see, I should be able to pull this up on here as well. All of this is more interesting. That's not what I wanted. Okay. All of this becomes more interesting when you try to solve some little less intuitive problems, and so this would be some of the current topics when you're looking at this. It's challenging to solve transient problems because solving the transient adjoint problem is very costly, because the adjoint problem is basically a backwards in time iteration. Turbulent flows is kind of the big question. How can we do this for turbulent flows? Something that I'm specifically working on, that's something I'm collaborating on with Dr. Trillian upstairs, is microscale topology optimization with microscopic boundary conditions. So what we do is here we use level sets and XFEMs for the boundary representation. And what we have is, at the microscale, a temperature gradient can actually create a slip along the boundary. Okay? And so as the surface is hot, the top surface is cold, which generates a temperature gradient along these fins. Okay? And that temperature gradient is going to cause the fluid to flow down the side of these fins. But it's really a boundary phenomenon. It's something that you would not observe at a macroscopic scale. Okay? And so what you can actually do is by generating smaller and wider channels, you're generating a high pressure drop in this direction, a low pressure drop in that one, a high one here, a low one here, high one there. You can actually pump fluid through these channels just by generating temperature, or by applying a temperature at the bottom and the top, or a low temperature at the top, a high temperature at the bottom. And so this optimization now said, well, if we start with this, what would be the optimal arrangement of these fins in order to get the largest amount of fluid flow through this channel down here? And so you can kind of see here the velocities are low, here the velocities are fairly high through the outlet. Now, this is more of a shape optimization than a topology optimization. So the next step of my research that I'm looking at is, how can I now take this step a little bit further and generalize this so that I don't have to prescribe these fins, but I can just tell it, do something. What would generate one of these pumps? And I'm not quite getting there yet. So, but that's something that I'm working on. And so for this case, I could not, there's no way I could solve this problem with a material distribution-based approach, because I would have this blurry boundary condition that just simply, all of this happens only because it's along the boundary. And I need the precise gradients of temperature and velocity along the boundary in order to apply this boundary condition. And so I really need an XFEM exact representation of the boundary. And even XFEM is limited. And so ideally, I would have body-fitted meshes, except that I don't know what the body is like that I'm going to fit. And so I can't really do body-fitted meshes. Because the problem is, if I would do a body-fitted mesh on these, I'd have to remesh every time, and then my mesh might actually give preference to certain designs, and so I don't want to do that. And so there's a lot of opportunities for different work to be done in this area. Let's see. Oh, we're still running. So we're still working on a little bit of an ellipse. It's kind of getting a slightly non-symmetric bump, which typically it would not. But it could just be that it's running on this small mesh. We can also see what it could also be that at this point we have not converged in our, we're actually diverging in our SCP. Okay, so the residual is 5.1 times 10 to the negative 3. .2, so we're still getting better in the residual. Okay, so the solution is still improving with this somewhat elongated ellipse, but you can see in this space is somewhat limited because I've decreased the number of variables, so I can't really represent a nicely smooth ellipse anymore, as I might if I use 100 by 100 points instead of 20 by 20 points. Okay. So I encourage you, look, if you're interested, look at some of these. Try to run a couple of these other ones. Kind of use this as a resource. Use me as a resource while I'm here over the next 3 months, if any of this is of interest. So, thanks for coming today, and enjoy the rest of the week. Thanks. Yes?
So your comment about meshes factoring certain quantities?
Yes.
So is that because there could be multiple minima? Because it's a problem at so if you assume sort of like philosophically that there is a perfect solution to a given problem,
Yes.
then a better mesh should approximate that solution better.
Yeah. Okay. So I think if the mesh is fine enough that it represents the solution accurately everywhere, okay, then it should be fine, and there shouldn't necessarily be a mesh or preference to the solution due to a certain mesh. Okay. But if my mesh, let's say, if I just were to start out and say, well, okay, if I were to start out and I say, I'm going to start out with a mesh that looks like this. Okay. Now my solution is going to be much better right there. And so, but if I would actually, if I would start out with a general problem, and then once the boundary refines in a certain area, or once I get some boundaries show up here, I should be able to do some sort of an adaptive meshing and refine the mesh around the existing boundary, and then every time the boundary changes, redefine the mesh. Yeah. So there should be some options there that don't really give. So what I meant was kind of a preference to a certain solution would be if I start out and I say, well, okay, I'm going to refine the mesh in this area, but not elsewhere. Now it's going to push it somewhere, possibly.